All right, now let's look what happens when we are no longer at standard conditions with respect to concentration. And we will be discussing the Nernst equation, which deals with this situation. All right, so consider our reaction here. We've seen it before. Let's consider it being a redox reaction. Note we've seen this equation, the change in Gibbs free energy under non-standard conditions equals the change in Gibbs free energy under standard conditions plus RT natural log Q, where Q is the reaction quotient. Recall from before, delta G equals negative NFE, E cell, under non-standard conditions, and delta G naught under standard conditions equals negative NFE naught cell. So plugging these into this equation, we get negative NFE equals negative NFE naught plus RT natural log of Q. If we divide both sides or everything by negative NF, we get E equals E naught minus RT over NF, natural log of Q, and this is our Nernst equation. Now, we're interested in what's going to happen when we have different concentrations. We want to keep the same temperature, so let's just go with 298 room temperature, 298 Kelvin. And when we do that, as we have seen before, RT over F is a constant. E equals E naught minus 0.0257 volts over N, natural log of Q. Now at equilibrium, remember, there's no transfer of electrons, so if we were at equilibrium, you would find that this equals E naught, and E naught minus this would be the same value, E would be 0 at that case. Okay, so let's look at our reaction here. We've seen this before in our first cell, zinc solid plus copper 2 plus goes to zinc 2 plus copper solid. Recall that our potential for this cell was under standard conditions 1.10 volts. So if we were to plug this into the Nernst equation, we wanted to calculate the cell potential at some other concentrations. We just plug in our E naught 1.10 volts. We see this as a 2. Recall this is a 2-electron process, so N is 2 here. Equals natural log of zinc 2 plus aqueous divided by copper 2 plus aqueous. Recall solids do not go in equilibrium expressions, so therefore we don't have to worry about those. That's pretty nice. And when you do this, what we realize is we've got this natural log function here, but whatever this number is, we're going to multiply it by 0.0257 and divide that by 2, which means the amount of zinc here, the concentration of zinc product, must be substantially more than the concentration of copper reactant for it to change the voltage so much. In fact, you can put the numbers in there. If the concentration of zinc 2 plus is 10 times the amount of copper 2 plus, means this reaction is over 90% of the way done. We got 10 times more zinc than we have copper in there. Then this ratio is 10, natural log of 10 times this number. What we find is our voltage goes from 1.10 volts down to 1.07 volts. When this reaction is over 90% done, our voltage only drops by 0.03 volts. So that's pretty nice. In order to get your cell potential to be very different from the standard potential, you have to have, the reaction must be very close to being all the way done. All right, let's use this information and let's look at this question here. Under the given conditions, will this reaction proceed spontaneously as written? Recall a spontaneous reaction, if it's a redox reaction, has a positive value for E naught cell. Well, here is our reaction here. Here's our concentration of cobalt 2 plus, the product, our concentration of iron 2 plus, the reactant here. Note starting out, we're going to have more reactant iron than we have product cobalt. So right away in this situation, this reaction lies to the left. We do not have more product than reactant. We have more reactant than product. This reaction's at the left currently. Well, we need to know if it's going to go spontaneously, which means we need to know if it has a positive E naught or a positive E cell. Because we're not at standard conditions anymore, we need to know if it has a positive E cell. So we need to plug it into our Nernst equation here. And to do that, well, we're going to need our cell voltage, we'll need the number of electrons, our concentrations we have. Well, if we look at the half reactions as written, here's our oxidation half reaction, here's our reduction half reaction, here's we get from the numbers and voltages we get from the standard table of reduction potentials. And what we find here is when we add up these two potentials, the oxidation and the reduction potential, that E naught equals negative 0.16 volts. Meaning, in general, under standard conditions, a negative voltage means this reaction lies to the left. Under standard conditions, the reaction lies to the left. We have more reactant. Well, okay, but we know that already. We have more reactant, more Fe2 plus. So from this position, will it go to the right, though? We already know this is already at the left, even though the equilibrium should be at the left. To do that, we need to say, okay, our potential currently is going to equal our standard potential, our negative 0.16 volts, minus 0.257 volts over N is 2, times the natural log of the cobalt 2 plus, which said is 0.15 molar, over the Fe2 plus, which is 0.68 molar. And so when you grind this out, you find out that E, our cell potential under these conditions, is negative 0.14 volts. Negative means it's non-spontaneous under these conditions. Cool. Well, the question is, when will this reaction be spontaneous? So what concentrations must our cobalt and our iron be to actually get this reaction to be spontaneous, to go to the right from the point that it is at? Well, to calculate this, we realize that this reaction is too far to, it's not spontaneous and under these conditions, so it's already under these conditions too far to the right. It's a negative voltage, which means under these conditions, this reaction will actually go to the left from this point. So it'll go to the left from this point. If we could calculate at what concentrations we would reach equilibrium, we would know that any increase in the iron concentration from the equilibrium point, any decrease in the cobalt concentration from the equilibrium point, would mean the reaction would go to the right from there. So we need to find out the concentration of Fe2 plus and cobalt 2 plus that would get us equilibrium. And so we can do that calculation using the Nernst equation. Recall, at equilibrium, E cell is 0. At equilibrium conditions, there is no transfer of electrons. Well, E naught is still our negative 0.16 volts. Do our math here, and we find that this ratio of cobalt 2 plus to Fe2 plus must equal 4 times 10 to the minus 6. So as long as this ratio is smaller than 4 times 10 to the minus 6, we have a lot of iron, less cobalt, and the ratio is smaller than 4 times 10 to the minus 6, the reaction will be spontaneous. All right. Now, if we're looking at this, what we find is these electrochemical cells that we've been making. Let's go back to our first one. And here's our zinc copper cell, and we put in a voltmeter here. And note, as soon as we have the wires going in, we have our salt bridge to complete the circuit. Electricity goes through this wire. What if instead of a voltmeter here, we put in a light bulb? Well, that means electricity would be flowing through the light bulb. A light bulb would turn on. So here we are converting our chemical energy, our potential energy stored in our reagents, into electrical energy. What we have here is a battery. Now, your book has a lot of batteries, examples of batteries, and so we're going to go through just a few of them real quickly. Realize that this isn't the focus of this class on how to make better batteries, but if we look at it, we have got our standard dry cell batteries, the batteries you find in your normal electronic devices, and they've got all the things. They've got an cathode, an anode, they've got this paste which acts as a salt bridge, They have everything in there, and they have the overall reaction for your dry cell and your alkaline batteries. Note that alkaline batteries are alkaline. Alkaline means basic, and we know with alkaline batteries, there's OH minus present. All right. In your car, you have a lead acid battery, and here's the reaction for a lead acid battery. Interesting thing about the lead acid batteries in your car is you need this battery to start your car. However, you want your car to be able to charge that battery up, and so the next video will deal with electrolysis, where we're going to actually use electricity to recharge a battery, to make the reaction happen the wrong way, because in your car this is the reaction that occurs. However, you have an alternator in your car that will provide electricity to force a reaction to run the opposite way. Now, there's a lot more batteries, rechargeable batteries, such as nickel metal hydride batteries. Lithium-ion batteries are the nice new batteries. They have a lot of benefits over our nickel metal hydride battery. And it even gets into fuel cells, the type of electricity generating mechanism that's used in the space program. There are some cars that are fuel cell cars. And if we can make fuel cells much more efficient, this is going to be the wave of the future for cars and lots of devices. A fuel cell simply just takes our overall reaction of a fuel cell. It takes hydrogen gas plus oxygen gas and makes water out of it. And the potential energy of that reaction is pretty substantial. But we don't want it to explode, so a fuel cell gets it to do that just by separating the two half reactions from each other and using the electrons to move through wires. All right. Well, we talked about, with our lead acid battery very briefly, getting a non-spontaneous reaction to go. In our next video, we will start looking at getting non-spontaneous reactions to go by adding electricity to the system.